Welcome back. So in previous lecture we discussed mostly about the fault topography, and at the end I was emphasizing about that we use the old satellite data to avoid the erosion and modification of the fault scarp while interpreting the particular regions towards the identification of active faults. So this is again you can use different methods using this is your satellite radar topographic mission data, and so what we will do is we'll try to come up with a lecture where you can use different techniques. Either you are using the ASTER data, or you are using SRTM data, or you are using the high resolution satellite data with stereo pair capabilities. So with that you can generate the topography of the area, and that will help you in identifying the landforms. This is another photograph close up of that same. You are having the terraces which have been displaced along the fault lines. You can see this. These are the scarp here. So this surface and this surface is the same and got displaced along this fault line. So there are two fault traces which have been seen, because usually what we take is that this could be an erosional feature, but if you look at the rivers which are flowing from uplands to in the plain areas, then what we see is that they are almost transverse to the alignment or the orientation of this feature. So you have a scarp. So if I just put in section here, then what you have is that you have a topography like this, and the rivers are flowing transverse to this. So if the river was flowing like this, then you may say that this is because of the erosion, but this is not the case here. The river is flowing like this here. Okay, so I'll exactly put this sketch on the topography here, then you will be able to understand much better. So you have the boundary here of the terrace. So you have a terrace here, and then you have the same here, the terrace, and this is the trace of the river channel. So river is flowing exactly perpendicular to the fault scarp. So this is your displaced surface. This is up, this is down, and this is termed as your fault scarp. So most of the in most of the cases we will be able to pick up such features if the area is active, and it's a different elevation in the landforms where we will not be able to find that the reason that this is because of the erosion, then those features are probably related to the active fault along the because of the deformation, ongoing deformation, and along the fault active fault traces. So surface manifestation of 1999 Chichi earthquake. The fault scarp can be seen here, and the fault trace runs somewhere over here. So this is your fault scarp, and this was along the reverse fault or thrust fault, the low angle, which was experienced at the time of 1999 Chichi earthquake. So this is from another angle. The photograph has been taken. So fault runs somewhere over here, and this block is up, and this is down, and this is what you see is the fault scarp. Another example of that. So you can see the displaced warped running track here, and you have the surface which is deformed. So fault runs somewhere like this here. This is the fault scarp of definitely the old fault scarp, but this got reactivated in 2005 Muzaffarabad earthquake. So you can see this portion is up and this is down here. Fault runs over here, and this is your fault scarp. So if you put the section, then you will be able to look at the topography something like this. Okay. So if I draw the block diagram, then it will appear something like this. So what you see is this fault scarp, and fault trace is somewhere over here. So this will be your fault trace, this will be your fault scarp. So whenever there is an earthquake, next earthquake, this will move. If this is, we classify this as an active fault, and since what we see here is your very young surface has been displaced, hence such features should be classified as active fault scarp. And this was identified long back in 1999 by Nakata from Hiroshima University, and this was named as Thanda fault in that region, and this was the causative fault for triggering 2005 Muzaffarabad earthquake. Further, coming to the Indian side, we will have detailed discussion on this particular side, but the fault scarp, if you see here, is this one. So you can field photographs based on that, you will be able to pick up easily the displaced landform. So you have the fault line runs here, and this is your fault scarp. Of course. So this is not a very good idea to construct the house on the fault scarp, which has been done without having proper understanding. So next event, this house will definitely be affected because of strong ground shaking. So this block is the hanging wall, and this is your foot wall. So again, if you take the section here, you'll be able to see something like this topography. So the house is sitting somewhere over here. And this is the topography which you see over here. And the fault which we identified and did the drenching is dipping towards north. And this is your south, this is your Indo-Gangetic plain. So fault topography basically is like what we see mostly will keep on recurring. Okay, and suppose the here what we see the terrace scarp, because the terraces are been displaced, and similarly we will come when we will talk about the detailed geomorphic markers, then we will talk about the terraces and the scarps here. So I will give one lecture on the fluvial landscape, which will help you in understanding that what are the terraces and what are alluvial fine surfaces and all that. But basically we will be looking at the displaced landforms which are comprised of the fluvial terraces. Fluvial, we are talking about the river deposits mainly, and the landforms which are sculptured or eroded or deposited formed by fluvial activities or the river activities. And then we will have the alluvial fan surfaces. Then we have, like what in one slide I was talking about, the back tilted surfaces. So basically what we will be looking at is the displaced landforms. So in this what has been shown that you have over the time you will have different displacement. Here you are having the terraces which are been formed by the river erosion and are getting displaced. So we term this as an these are the terrace scarps, but this is the fault scarp here. So you will have to differentiate between the primary and the secondary features. Okay. So this is because of the erosion by the river. So this you have the terrace scarp, and this marked in red is your fault scarp. Now time prediction model was given long back in 1980 by Nakata and Shimazaki. So this is required because when we are talking about the hazard assessment, so risk of future earthquake occurrence is estimated based on time prediction model. So when will be the next earthquake on a particular fault and what will be the magnitude, that is extremely important. So time prediction model presumes that the slip rate of the active fault is constant during late quaternary. But this remains a question, okay, the slip rate on the active fault. So what we have learned from our investigations that the slip never remains the same and the magnitudes never remains the same. But the prediction model assume that the slip on a particular fault remains the same and similar magnitude will be triggered every time. Whenever there is a next earthquake, the similar magnitude earthquake will be triggered. But it is better to take into consideration the maximum amount of slip recorded or registered on that particular fault. So three types of predictable models are suggested: a regular slip and time predictable model, time predictable model, slip predictable model. Okay. So these are the three different type of predictable models are been suggested by Nakata and Shimazaki in 1980. So if you take the regular slip and time predictable model, then in one of the lecture in the beginning we talked about that if you have an similar amount of strain which is getting accumulated along a fault, then at a particular time which is more or less similar between the two events, at that time it will slip. Okay. So this what it shows is again you have the time here and you have the displacement. So over the time the strain will develop and then you will have an earthquake. Over the time the slip will develop and then you will have an earthquake. So if you have the regular slip and then with the help of the averaging, you can even predict that when will be the next earthquake. Okay. So this shows the last earthquake event, and these are all 1, 2 and 3, and fourth one you can predict that when the next earthquake will occur, considering the average slip on the fault plane. So you with this at least you can consider the varied slip observed between the during different events and take an average, and you can predict the. So this is the model which shows the regular slip and time predictable model, whereas the time predictable model mainly does not take into consideration much of the amount of slip. So here what has been shown at that you have the earthquake with the less slip here, that is displacement, but the another one was with the larger slip as compared to this one in a very short period. So this also helps us in understanding that if the entire accumulated strain or the energy is not been released during or it has been released by a small earthquake or moderate earthquake or large magnitude earthquake, then the actual slip is available, or you can say that the slip deficit will trigger another earthquake in very short period. So you have so between because it has a smaller earthquake here, then immediately in a very short period you had another one, but even when after having the large displacement or the large magnitude earthquake, because the displacement will also tells us about the deformation or the amount of the amount of energy released, and that is directly related to your magnitude. So large amount of displacement, hence the time which was been taken between the next earthquake was comparatively larger. But then also with this best fit line, you can predict the time of the next earthquake. So this is based on the time you can do, and first one was the regular slip and time prediction. And slip prediction, basically if you take, then you can have very much similar to that, but yes, here what we are getting is the time is not the same. Okay, you can have, but you can. So what does this indicate? That you had between this and this earthquake, you will have very much similar time which has been taken, but the slip varies in different earthquakes. Okay, slip is not doesn't remains the same here. The displacement is less here, displacement is less here. So what one can suggest is that this was for example type 1 earthquake, and this is your type 2 earthquake, and this is very much similar to your type 1 earthquake. Now this 2 you have based on the slip. So what you expect is that the next one will be your type 2. And this is what exactly has been predicted for the earthquake after 2015 Gorkha event in Nepal. So what the scientific groups believe that this was like 7.8 or so. So next event will be very much similar to 1934 earthquake, and this was magnitude 8.2 or so. So you can predict the next big earthquake based on the slip prediction. So what we do is, after identification of the surface deformation, old surface deformation preserved on the surface, or rupturing along the rupturing fault, then we open up the trench to understand the pattern of displacement, the pattern of slip, and that what we call trenching. Okay. So this is the technique which we will discuss as we move further in this course, but just to have a brief understanding, we can quickly look at what we see here. So if you can see here is that we again use the knowledge of the sedimentology, and so we have used this as geomorphology part, and then what we are looking at in this section is the stratigraphy of the succession and the structural geology we use, because we are looking at the folds and all that, and the property of the material. So grain size, color, everything we will be able to say. So this we can classify this as soil here, humus rich soil on the top, and then this layer goes somewhere over here we have, and then the contact, that is the discontinuity between the two units is very clear here, and this portion which has been seen folded is comprised of gravel here. This is sitting somewhere over here. So this is the net displacement what you have, and this portion is your the shear zone along which now the faulting has taken place. Now in this example, it shows that the displacement, this layer was not displaced and the faulting remained blind, okay. Whereas there is a displacement between this layer, but so this is a penultimate event, but the recent one you don't see the displacement reaching right up to the surface, but of course the deformation has reached. So this we can say the earthquake was on blind fault, and the earthquake remained blind. Coming to another one is your strike slip, and as we have discussed that it is the lateral movement along the horizontal plane. So geomorphic markers associated with strike slip faulting environment, if you look at, then what we see is the offset of any surface feature. And this is an example from 1979 Imperial Fault earthquake, where the trace has been seen here, very much similar to what we were talking in for the examples or the evidence of 1995 earthquake surface rupture. Here also the agricultural field has been displaced along this line. Okay. So this is your fault line, and the displacement you can easily make out over here. Okay. So you have this one here, and this one is here. So the landforms, basically what you will come across along the strike slip fault, that is the geomorphic signatures. Okay. So in mostly the thrust fault and the reverse fault, you will be able to see the formation of scarps. Okay. So if you are having, for example, the horizontal surface here before deformation, and then after the deformation, in case of the reverse fault, what you will see is you will have the fault scarp which has been formed like this. Okay. So you have the fault which is sitting here, or to be slightly precise, over here. So this block has moved up. Now in case of the normal fault, okay, so in this case this portion will go up. This is going to be the footwall, but in case of the normal fault, this block will move down and this block will remain the stationary. So the feature, again, what you will be able to see will be something like this in case of the normal faulting. So you have the fault is here. So the topography which you will see in the normal fault, so this is in the case of normal fault, and this is in the case of reverse fault, or you say thrust fault. Okay. So here we are having compression, and here you are having extension. So this prominent topography is very much similar in the case of the normal faulting and the reverse faulting, but in case of strike slip faulting, which will have the component of so the strike slip faulting will have the combination of normal faulting plus lateral faulting, okay, and or you will have reverse faulting plus lateral faulting. So you will have combination of this two. That is what we call the oblique slip. So this oblique slip will and the will result into the formation of different landforms with a combination of the scarp as well as the lateral displacement or the deformation of the features on the surface. So, for example, what you will see is the formation of the linear valley along the fault trace. Then you will have scarps, you will have benches which have been developed, okay, like the multiple scarps here. Then you will have sac ponds. This I will talk more in detail later on, that how sac ponds are been formed, and the shutter ridges. So, and the you will have offset. So, these are a few geomorphic markers are extremely important, which I'll put as a box here, so that you will be able to. So, anyway, but these are like linear valley, scarp, sac ponds, and then offset of drainage is important, and the shutter ridges. Okay. So, these are some very important parameters to differentiate between the different type of movements. What we see as one is on the either it is reverse fault, normal fault, or in strike slip fault. So, as we have been discussing about that right lateral and left lateral, so this slide will make things a bit clear about the sense of movement, what we classify as a right lateral and left lateral. So, right lateral strike slip faults are termed as dextral dextral slip fault, or with it shows the dextral movement, and sinistral is for the left lateral strike slip faults. So, this figure it shows the offset or the deflection of the channel along the black line, that is your fault line. So, movement is the stream is flowing like this, getting offsetted here, and then again flow straight here, then again. So, if you are having zone of strike slip fault, and then you will see multiple fault lines and the displacement very much similar to what has been shown here. So, this is in case of the right lateral strike slip. That means you are looking at the dextral movement. So, in a simplest way, if you see this, then you are having the dextral. So, right block is moving towards your side, and left block is moving away, and this is your fault line. And in this case, the right block is moving away and the left block is moving towards your side. In case this one is the right here. So, in this case you have what we say the dextral moment, and in the left lateral we say sinistral moment. So, this things you should keep in mind, that if you are having left lateral, then you say that is in your sinistral moment. So, similar to what has been shown here, the offset of rail track. So, whatever so this is a man-made structure which has been shown with the sketch, that they got displaced during the whenever there is a movement along this fault, depending on what type of movement will take place. Of course, the strike slip remains the same, but you will have either it is sinistral moment or dextral moment, and the landforms which are with that those exist on the surface will also get deformed and modified depending on the type of movement. So, for example, if you have like if you just put in stream here, which is flowing straight, and now you are having a stream like this getting bent here and then flowing. So, this will be your left lateral movement, or sorry, right lateral movement. And when in case of this one here, if you are having like this, then you have the left lateral movement. So, if the fault is passing through this area, then so this part you can keep in mind. So, you have this is your dextral and this is your sinistral. So, dextral movement and sinistral movement. So, this also I have shown in one of my lecture. One of the best example on the earth surface is the right lateral strike slip fault, and that is your San Andreas fault system in US. and this is between the North American plate. The deformation is due to the tectonic boundary between the North American plate and the Pacific plate. So what you see here, there is an aerial oblique photograph. So you see the scarp which has been developed here, a very linear valley or the trace of the fault here, and then you have the streams which are been offsetted here. So this shows the offset, amount of offset of the stream, and even smaller stream are getting displaced here. Now this portion, if you see carefully, has blocked this channel here. So this type of features are termed as shutter ridges. So they are acting as a shutter in front of the channel which are flowing across the scarp here. So this portion of course is up, this is down. So this portion is up, this is down, and also we see the lateral offset along this fault. Okay. So then in this case, I hope you will be able to easily recall that what type of fault in total we will talk about. So this is your oblique slip fault. This is another fault scarp which has been seen over here. Of course, you see in this all this exists, and then this one is the fresh one. Okay, so this is the latest event or latest earthquake. This scarp has been formed. So this what total, if you see, is the cumulative scarp. So this side is up, and very fresh straight scarp has been seen. This side is down, and this indicates your normal fault scarp. So in case of the topographic break, if you have to look at on again on a very large scale, this is again an aerial photograph, but the contact which has been shown for any active deformation will be very sharp with respect to the geomorphic in case like what we are talking about, the geomorphic boundaries. So very sharp geomorphic boundary between the uplands and the plain areas. So this marks the trace of the fault here, and based on such interpretations at the initial stages, you can mark that this is area which is going to have a potential active fault, and further detailed studies or the close-ups of that you can take and try to identify the fault scarps and other related features. This we have already discussed, we will just go ahead, but the important part here is that this is the fence which got displaced in 1906 San Francisco earthquake. But the features which have been shown here, along with the linear valley, along the fault line, is your formation of the linear valley, then offset of streams which have been shown here, and the formation of sac pond. So the most common and important features which we will pick up to classify at least that this is the strike slip active fault are these three features. Okay. So if you are able to see the sac ponds, you are able to see the offset of stream and formation of linear valley. So these are the two most important one. So the movement here is again you are having this offset of streams. So the movement is your right lateral strike slip movement. Again similar one. So whatsoever the landforms you see on the surface or are present on the surface during the deformation will be deformed or will get offsetted along the fault plane, and that will along the fault line, and that will be preserved, will remain preserved. Either they are ridges. So this shows the offset of ridges here. So this is the top of the ridge line here, and then this goes somewhere over here like this, and similarly the ridge line is here, and then this shows the offset of streams. So all the streams which are present on the surface along this fault line are displaced or offsetted. So again this streams have moved like this. So you have the right lateral strike slip. Now as I told in one of the lecture that either you stand here or see that what type of movement has taken place, whether it is right lateral or left lateral, it remains the same on both from both the sides. Okay, you see. This also we discussed. This is because of the creeping of the right lateral slip here. So you see this is an offset along the fault line, and similarly this also we discussed. So I have a couple of photographs which I have already shown you in one of the lecture from Hayward fault, which shows the creeping. The fault runs here, and on the surface we see the offset. So that was with the stream offset, and this is related to your offset of man-made structures. This also is the close-up of that. So I have already explained this, so I'll just go quickly ahead. So you have an offset here. So you have the offset of the pedestrian path, and similarly the offset of the rail track. Thank you so much.